Hello everyone, welcome back to Machine Learning with TensorFlow. In this tutorial we'll learn about Keras, how to code in Keras. So what is Keras? Keras is a high-level library which can run either with TensorFlow or Theano. TensorFlow or Theano will run in the backend. In Keras, each layer requires only one line of code, which makes it really simple. We do not have to specify matrix multiplication or matrix addition as we have done in TensorFlow. Moreover, we can also integrate the activation function in the code of the layer. That makes it very suitable for deep learning. So what is deep neural network? So far we have seen this sort of network where we have only one hidden layer. In deep neural network, we have more than one hidden layer. You can have as many layers as you want. For this example, we will try to predict a future value of a sine wave. So what does that mean? For example, we are currently here. We will try to predict a value near here. So when we'll go to the next step, we'll try to predict another value here. So we can understand that the output is a shifted version of the input, just like this. In general, it is always better to use more than one input sample to predict some values in future. For example, you may want to predict something 5 steps ahead, and you may think about using only the present value, but it is always better to use the previous value and the value before that and some more value before that. To serve that purpose, the one-dimensional input vector is converted in a two-dimensional shifted matrix. For example, if you have an input vector like this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we will create a shifted matrix like this. The first row will be the same as the input vector. The second row will be shifted by one sample. The third row will be shifted by 2 samples. The fourth by 3 samples, and so on. After shifting, we will feed the first column as the first input, and after that we will feed the second column, and after that the next column and the next column. So that will contain the present value as well as the previous values. We can choose any amount of shifting for the input. That means we can use any number of previous samples. So let's go to the code. In the code, at first we will import the sequential model from Keras and the dense layer from Keras. We'll also import NumPy and matplotlib. So let's run this cell. We will define a function called shift vector, which will give us the shifted two-dimensional matrix. Let's run this cell as well. In this cell, we will create the training input and the training output. To do that, we have created a time vector, and after that we have passed the time vector through the sine wave. If we plot it, we can see the relationship between the input and the output vector. And till now, our input vector is a one-dimensional vector. So in order to have the two-dimensional shifted matrix, we will pass the training vector through the shift vector function, and we want 5 rows of shifting. So if you print this vector, you will get something like this. After that, we will transpose the shifted matrix, and after transposing it will be suitable to feed only one row at a time in the network. The first column gives us the original training vector. The second column gives us the training vector shifted by one sample. The third column shifted by two samples, and so on. We might have noticed that we have padded some zeros to create the shifted matrix. As the size of the input is changing, so we need to add some zeros to the output as well, so that the sizes of the input and the output remain same. So we are adding 5 minus 1 zeros here. Let's run this. After that, we will define our model. To do that, at first we have to tell what type of network we are going to build. Here we have told the compiler that we are going to build a sequential model, and after that we have added a dense layer with 64 units. That means 64 neurons with an activation layer of ReLU and an input dimension of 5. This input dimension is important for the first dense layer. Next, we are adding another dense layer with 32 units and ReLU activation. At the end, we are defining the output layer as another dense layer with only one output and a linear activation. We definitely have to define the loss function and the optimizer we want to use. The matrix shows what are the information we want to see during the training process. At the end, we tell the model to fit based on the training input and the training output with only 20 epochs, and we will use a mini batch training for this purpose with a sample size of 20. So for every 20 samples the weights will be updated. Let's run this one. If you have a look at the loss, you can see that initially it is around 0.356. At the end of 20 epoch it is around 0.001, which shows that the loss has decreased significantly. That means our network has learned the relationship between the input and the output very well. To test that, we will feed the training input in the model and we will get the output. If we now plot the calculated output and the actual output, we can see that the difference is very small, which means that our training process is acceptable. So that's it for today. Thanks for watching.